Okay, we are going to start Chapter 3's PowerPoint. Chapter 3 is all about energy. So this is probably one of my favorite topics just because I find it pretty interesting. So of course, we're going to have to go through the core concepts at first. Energy is transformed through working or heating, and this is just showing a picture of a dam because I don't know if you've ever been to a dam before and actually gone into it. If you haven't and you're from around this area, you can go to the Pensacola Dam over in like Langley, Disney area, and they actually have tours underneath. But it's just really neat to see because it has a whole bunch of turbines, and it's going to collect a lot of energy. So obviously there's water that's behind the dam. If they release the water, then that can create energy. And then we'll also talk about the energy before the dam is released and then after it's released, and how that relates to both potential and kinetic energy. So one thing that we do need to know for energy is conservation of energy, which we've heard that word a lot, conservation. So same thing here, just energy is not created or destroyed, it just is. And it can be transferred from one type to another. So we see it as work or motion. It can be based on position, that's your potential energy. You can talk about things like light, that has to do with energy, heat, chemical, nuclear energy. Some sources that we get energy, we'll talk about this in a little while throughout the chapter, is things like petroleum and coal. And of course with the dam we've got moving water, we've got nuclear power and solar power. So all pretty cool stuff right there. And then it's used in things like, obviously, transportation. We have to have energy in order to, drive our cars. Generation of electricity. Thank goodness for electricity, right? Heating, cooling, lighting, things like that. All right, so the first type of energy or manifestation is work. And so this is your first equation for the chapter. So I would encourage you to print off those PowerPoints I put on, I believe it's on module or week 4 on your Canvas. And so if you would print those off, and if I was printing them off for you, I would suggest to do 3 slides per page, and then it kind of has lines on the side. It's just kind of easier to work with, in my opinion. But you do it however you want, obviously. All right, so first we've got the definition of work, which is just the applied force through a certain distance, and it has to be a parallel distance. So if you look here, you can see this force and this distance, they're parallel to each other. If you were to do a force and a distance like this, there would be no work involved. Okay, so kind of keep that parallel word in mind. And then work is equal to force times distance. So this is your first equation. And we're going to, go to the next slide really quick. And units for work is going to be measured in joules. And obviously if there's zero distance that's happening, then there's no work. And anything that's perpendicular, so like I told you earlier, if it was like this, then there's no work there. It has to be force and distance being parallel to each other. Okay, so it kind of shows you over here below this picture, but I'm going to write it out again. So work is equal to force times distance. Do you guys remember what the unit for force was in chapter 2? Force is measured in newtons. What do you think distance is measured in? Distance is measured in meters. Let's break it down a little bit farther. So newtons is kilograms times meter per second squared. and times a meter. So that ends up equaling kilograms times meters squared per second squared. Whoops. Which is this is our new unit for energy or work, is a joule. Okay, so this is a joule. And work, do you think it takes energy in order to do work? Right now, as I'm doing this video, it's taken some energy for me to actually do this. And so even just getting out of bed, right, is going to take some energy. So work and energy are sort of interchangeable type words. And they're both measured in joules. All right. So I do think that there is a little example here. Yep. All right. So I'm going to bring up the book really quick so you guys can see what I'm talking about. What is going on with that? I have no idea. I don't know. Let me get rid of that really quick. Let's see if I can cancel that. Well, crud. Don't we just love to have technical difficulties? Let me see here. So if you go to your McGraw-Hill and you go to, obviously you don't have a whole bunch of courses going on there. Go to your resources, go to your book. So if you didn't know how to do all this, there you go. All right, so we've got our chapter 3 book here. And if we go to our first example, and I'm going to actually bring up my little note thing so I can write on it here. I'm having all kinds of technical difficulties right now. I don't really know why. All right, let's go back and it's not letting me do anything right now. Of course. Well, let's kind of read through this. I don't know. I think it's freezing up on me. Let's just read through the example for a minute. So we've got example 3.1, and it says how much work is needed to lift a 5 kilogram backpack to a shelf that's 1 meter above the floor. So it did specifically say work, okay? And it says to lift a 5 kilogram backpack. I think it's gonna let me do this now. I said that and now it's not. Ugh, I don't like technology. Okay, here we go. So it says that we've got a 5 kilogram backpack and it's being lifted to a shelf that's 1 meter above the floor. All right, so this is pretty simple. So work is equal to force times distance. Now, I said it's pretty simple, but there is a little bit of a catch here, because am I given a force? Are either of these two things a force? Well, 5 kilograms is mass, kilograms is mass, meters is distance. So I have distance, but I do not have a force. How in the world am I going to find force? So this is something that you have to kind of go back to chapter 2 on. And this is really going to probably make you mad, because this W stands for work. Well, you remember back in chapter 2 how we had weight was equal to mass times gravity, and it's also a W, unfortunately. People always get mad about that. Like, I don't make up this stuff, guys. I just have to, teach it. But anyway, so if we find weight, do you remember what weight was measured in? Not to be confused with mass. Weight was measured in newtons, not pounds, because we're not
talking about English system units, we're talking about metric system because we're in science class. Okay, so we just take our 5 kilograms times 9.8. So we're going to assume that we are on the Earth. And whenever you do that, you're going to get 49 newtons. Okay, so that gives me force. So now I can go and I can do this. So I have 49 newtons times 1 meter, which is 49 joules. Okay? A Newton meter is the same thing as a joule. All right. I don't really like example 3.2 because it's doing English system units, and the whole time in chapter 1 it's telling you how we use metrics. All you have to do on it is it's basically already got your work on example 2.2. I'm sorry, not your work, your weight, because it says 50 pounds, so you don't have to convert anything there. A foot-pound, okay, is also a unit of work, but I am mostly just going to focus on metric system stuff just because I don't really want to confuse that situation too much more. Okay, so hopefully this example 3.1 wasn't too bad. All right, I'm going to go back to the PowerPoint because we got to get to power really quick. So actually, there's a little bit more work apparently. Oh, this is just showing you how it has to be in the same direction. So the maximum work, this is showing you like if the force of the wind and the distance, you know, is going the same way, then you're going to be flying through the air pretty fast. If you have some force that is kind of going at an angle, or it's even going perpendicular, you're going to have a lot of reduced amount of work. Okay, so parallel is key there. And then I forgot about this too. This was also in this section, simple machines. We're not going to get too much into simple machines, but I do want to kind of talk about them a little bit. Basically, think about lifting a box. You're going to have to pick up, let's say you're going to have to pick up this box. So you're going to have to put some work in order to pick it up. And if you pick it up, then you're basically lifting its mass, right, or its weight. All right. Well, sometimes that's really difficult to do, especially if the box is like pretty heavy and there's just you. So you can kind of see this picture right here of this person, and they're picking up this 300-pound mass by just pushing 60 pounds of effort. So how is that working for them? Well, they're using a simple machine. We probably look at it and see like a teeter-totter type of situation. And if you think about, you know, when you're on the teeter-totter and stuff playing, you know, if you don't have the same mass on both sides, then it doesn't really work very well. But if you start moving one of the masses closer to the fulcrum or to that pivot point, then it does start to help. So I want you to kind of know some of these simple machines. An inclined plane, you know, kind of like a ramp, a wedge, kind of like this fulcrum, a screw. It's kind of considered an inclined plane too. A lever is like sort of like this board, or even if you think about like a hammer, the long part of the hammer is the lever. A wheel and axle, so think of like a wheelbarrow. That wheel is typically like, you know, on the end, and then it's got this, I'm a terrible drawer, it's got this wheelbarrow here, and then you've got this lever, and you can put a whole bunch of stuff in there, right? And then you've got like a pulley system, and you can do a whole bunch of work based on how many pulleys you actually have. And this is kind of showing you like a pulley system in this picture. So we're not going to worry about that equation right there, okay? I just kind of wanted to go through some of the simple machines with you and just tell you that whenever you do use simple machines, you do kind of, it does help you, and you can actually put in a lot less effort and lift a lot more, okay? But it does matter how long, like the lever is, and because if you think about it, this distance right here is, if it's greater, if it's a long distance and you put in a little force, then you can lift a pretty big force that has a small distance from the fulcrum. Okay, so but we're not going to go into calculating or anything. I just want you to know some of the simple machines, okay, and kind of the basic idea. I think I'm going to start another video for power